Hi, and welcome back to the video series on deephaven.learn. In the previous video, I covered considerations when moving from static to real-time data. Most importantly, I discussed the batch size as well as what incoming data looks like in real time from the perspective of deephaven.learn. In this video, I'll go through what many consider to be the hello world of AI and machine learning, the iris flower classification problem. This problem can be easily extended to work in real time with deephaven, so I'll show how that works. To do this, I'll be using deephaven with scikit-learn to implement a k-nearest neighbors classifier, or a KNN for short. The model will be fit on a static dataset and then tested on a real-time feed of simulated iris flower measurements. This will be done using two scripts. The first will do the model fitting and validation, and the second will do the testing on the real-time feed. All of the code I'm about to cover exists on our docs website, for which the link can be found in the video description below. First off, I'll touch on the import statements. From deephaven, I import learn and learn gather for obvious reasons. I also import read CSV to get the iris data, as well as dynamic table writer and types to simulate the real-time iris measurements. I only need one scikit-learn import, and it's the KNN class. Lastly, I need numpy, random, threading, and time. NumPy is used by learn gather, and the final three will be used to simulate real-time data. Next, I import and quantize the iris dataset. The KNN will attempt to classify a flower based on a set of measurements, and that classification will come in the form of an integer number. Thus, I quantize the iris species column into a set of integers that correspond to each unique flower type. Next, I create a global variable, which I call nay, short for neighbors, and two functions. The first function will fit the KNN and save the fitted KNN to the nay variable. The second will loop through a set of observations and use the fitted KNN to classify each of them. Note that in the second function, I have to ensure that my observations are two-dimensional. Machine learning models typically expect input data to be of a particular shape and dimensionality. In the next section, I define three helper functions. I have two gather functions and a scatter function. First off, I have table to array double, which will convert a subset of table data to a two-dimensional NumPy array of doubles. Next, I have table to array int, which does the same, but the NumPy array contains 32-bit integers instead. Lastly, I have my scatter function called getPredictedClass, which simply returns the integer value of the model's predictions. In the first learn function call, highlighted here, I fit the KNN to the entire iris table with the quantized classes. I specify two inputs. The first is the set of observations, and the second is the quantized classes. Thus, I have two learn.input objects. The observations are of double type, so I use table to numpy double, and the classes are integers, so I use table to numpy int. The second function call, which is the final part of this script, uses the fitted KNN on the same dataset so that we can see how it actually performs. Scrolling through the iris KNN classified table will show that the model performs pretty well. I'll run the script now, and we'll see how the model performs. We take a look at our class column. These are the actual classes that belong to these measurements, and the classified class column is the results of my model's predictions. As we can see, the model gets almost everything right. We can see a couple of cases where the class is actually 1 and my model thinks it's 2. The same goes for 2 and 1. However, this gets the vast majority of them right, and for now, I'm satisfied with these results. So we'll move on to the next script. This script can be broken into two sections. The first sets up and starts the real-time data feed. I won't go into detail on this, but it uses dynamic table writer to write a simulated iris flower measurement once every second for 1 minute. The simulated measurements pick random values for each observation between the minimum and maximum for their respective columns. For more information on how to use Dynamic Table Writer, check the video description below for links to our documentation. Lastly, we have the learn function call where we use the fitted KNN on the real-time feed. I also use the helper functions originally created to work on static data, and as we'll see shortly, they work on real-time data as well. This time around, I have only one learn.input object, since I don't know what class these simulated measurements actually belong to. I only receive one new measurement per second, but in the case that I wait a long time to run the learn function call, I set the batch size to 150. When I run this script, we'll get a real-time table of simulated measurements as well as the live classifications. Here's my simulated measurements. Here are my live classifications. This could go on for 60 full seconds, but we don't need to watch all 60 seconds of it, so I'll wrap this video up shortly. That's all I have for this video. There's only one left in the series of guides, so if you made it this far, I appreciate you keeping up with it. In the next video, I'll actually write up a script to perform moving window operations on a feed of stock prices. Like and subscribe for more content like this, and thanks for watching.